Hi, friends. Sorry if it was just a long wait. It didn't beep in that it was going until just now. So I want to go over the POGL. Usually when we do POGLs, we kind of do them as one-way assignments where you're kind of going over something we talked about. I don't want to double up on this section with notes and this, so we're going to kind of do our notes through this POGL, okay? And what I mean by that is we're going to kind of go through it. I want to talk through it, and I want to hit some really important points. I want to make sure that you know the answers to and that we can think through, okay? So there's three models here in this POGL. Model 1 is referring to these types of molecules here and how they interact maybe with our cell membrane. And taking a look here, we have ions, we have type 2 molecules, type 3 molecules, type 4. So we kind of have to figure out what they are. So first, ions. Ions are small charged particles. So we might want to write charged right here. I don't know if they have you guys do that during this thing, but they are charged particles. Our cell membrane does not do well with charges. It kind of sends them back because the charge is very much like polar. Most of our cell membrane is nonpolar, and so these guys need a actual design channel to get through. If we're talking about passive transport, if we need just like movement without energy, we need a channel. If we need to do this active transport, we need a pump. Okay. Type 2 molecules, they're large and they're polar, and so they struggle to get through. They're going to need something to help them get through because they're just so big, and also because they are polar. So glucose is a great example of this. Type 3 molecules, they are small and they're polar. You can kind of guess that they're polar because water is part of this. They're not as big as this. Urea is also polar because of the oxygen and the nitrogens here. And these guys are non-polar and they are small. Why they're non-polar? We haven't talked a lot about O2 and CO2. But because oxygen is a bully, but it's bullying itself on the other side and ends up being non-polar. And the same thing here, carbon can't really get bullied, and the amount of bullying it does get bullied, this oxygen is pulling electrons this way, this oxygen is pulling electrons this way, and it balances itself out and makes something non-polar. So polar, small charged particles, polar, large particles, polar, small particles that aren't charged, and non-polar small particles. And when we look at the membrane here, this is the waters. You can see the kind of the shape, or maybe we can even say, this is CO2, sorry, my bad. CO2 here, you can see the oxygen, carbon, oxygen. They can get through very easily. If you're nonpolar and small, you can get through this membrane super simple because these heads here are polar. We learned that a couple weeks ago. And these tails are nonpolar. So these guys can go in and out like no problem. This right here is going to be a glucose representative. It struggles to get through. It really, truly struggles. And so it's going to require probably a channel to help us through. Like we got one through, but that's not nearly enough. You can see here, these are urea. Again, it's going to struggle to get through. It's going to need more assistance than something like CO2 here, but it does get through decently, not great. So we have channels for these guys. There's a famous one for H2O. It's called aquaporin. Aqua means water, porin means pour. They're all over your cells. They let in water and let out water based on what the cell needs. And here is the charged particles. You can kind of see that they can't even get through no matter what. So it's kind of like a scale. Charge, can't get through no matter what. Big polar ones, by chance, they can get through. Small polar, really kind of resist them, but a little bit of a flow. And then the CO2 and the non-polar small ones can get through no problem. Oxygen, CO2, that makes sense. We don't want to delay oxygen and we don't want to delay CO2. We want them to go in and out all the time. Going forward here, we can see embedded proteins, so maybe this can help us get through. And this is how we're going to get all these guys through right here. We're going to use these little protein channels to get in and out. Each protein channel is actually designed for each specific thing it's getting through, so it's not like this positive charge ion can get through this guy. It's really just designed for urea, it kind of goes along with that lock and key model that biology loves to use, that each single channel has its own guy that it lets through, but nobody else can. So we got to think about it that way. And then they gave us some more ones down here. So let's take a look at these guys. Nitrogen gas, N2, that's going to be a nonpolar small guy that goes in and out really easily. H3O is a charged particle. It's small, it's polar, it's going to struggle to get through. Alanine, if you can see here, here's the amine group. Here's the carboxyl. Here's the R group. So the R is nonpolar. So this is a large nonpolar item, which doesn't really fit anything up here very much. I would say the only thing it kind of fits is this guy a little bit, and this guy maybe a little bit because he's so large. So it's kind of actually a new classification here. But this guy will struggle to get through just because he is kind of bigger, and he does have some polar parts. You know, he does have some polar parts, even though we consider him non-polar because of this guy. Sucrose, this is a sugar. You can see how polar and large he is. This guy's going to struggle, really struggle to get through. I think it's a 0 chance. Glucose is just small enough to get through, but with this extra fructose added on, it's going to be a burden. And then bicarbonate, again, you can see it has a charge. This is very polar. I would say I'd put it in the small polar bin. Really, to be a charged particle, you have to be an individual charged particle. So we'll probably put them in here. There. So I hope this kind of makes sense. You go through, you answer your questions, kind of make sure you understand it. Tonight, if I pull up the actual assignments for today, we're kind of doing this in class. And then tonight, I'd like you guys to read. We're going to have a reading quiz over 5.2. I'll even put 5.2 on the thing. And you can take notes on it, and you can use your notes during the quiz. So it'll be important to do that. But basically, what we're going to work ourselves into is we're going to work into tomorrow and a little bit of today, diffusion, and then osmosis on Friday and Monday. And then next week, we kind of get ready for the test that's on Friday. So I hope that makes sense. If you guys need any help, let me know. Thank you, guys.